My name is Rian, and so the title of my hack is Temporal Memory in Racket. And so what I'm essentially going to be talking about is how one might implement the new temporal memory algorithms that Chaitin recently released in a programming language called Racket. So the reason I chose this hack is actually kind of selfish. I wanted to really get a good understanding of how temporal memory works and really dive deep into the algorithms, understand every intricate detail, because that's just how I work. And so one of the other sort of issues I had, at least sort of coming from a mathematical and Lisp background in general, was I wanted to do something that was functional. And essentially, you know at every moment in time what your inputs are, and you can use those inputs directly. So essentially, it's all about purely transforming information from one data structure to another, and that was sort of really interesting to me. And what I absolutely did not care about was speed. So this is really a toy implementation. I just want to see something work and make sure that I sort of understand this entire process. So that was not an issue for me at all. So that's sort of why I favor clarity over speed, at least for now. So I don't expect this to be in any sort of commercial or production setting. And I guess the reason I kind of like Racket is, we had a presentation on Closure, which is also another modern Lisp. Actually, Racket is being used right now across many different middle schools and high schools as their first programming language. So I feel like a lot of students are getting into this language very young. And I am also consider myself a novice programmer. I've kind of been at it for less than a year, maybe 9 months. And so the motivation for me to start programming was, on intelligence and these algorithms. So I had tried a couple of times, but finally I got to the point where, HTM stuff is enough motivation to really sort of kind of just go at it and learn to try and implement something. And so this is sort of my first program.
Whoa.
Wow. Mine was Hello World.
Well, I did that too, but I don't know. But yeah, and so the other thing I want to talk about what makes Racket unique amongst not only the Lisps in general, but all languages, is that there's a really succinct, I don't know, natural language is very important to this community. There's a very succinct mapping between how we represent natural language and how we represent a programming language. So in essence, in Racket, everything can be thought of as a domain-specific language, as I'll sort of get into briefly. And the idea is that over time, essentially, you end up creating code or program that essentially fits or maps to your program. So it's essentially you're evolving code to fit or solve your exact problem. And that, I think, is pretty cool. So those are the whys. And now I wanted to just touch on some of the differences between the implementation that I'm working on and Chaitin's implementation in Python. So there are not that many differences. I essentially wanted to make sure that the mapping was as close as possible, but there are some slight deviations. So first, in Racket, there are no classes at all. So like I mentioned before, it's just pure information moving from point A to point B. So that's the first thing. The other way is sort of how you iterate your functions. And or at least I like recursion. Recursion is kind of, you have a love-hate relationship with it. Some people love it, some people hate it. Actually, there's this cool quote I found: "To iterate is human, to recurse is divine." And it just kind of goes along with sort of your own philosophy. But you can do a lot of really interesting things with different types of recursive techniques that are a lot more difficult to do with using different types of loops. And the other thing, and kind of what slows this implementation I'm working on, is that I wanted one uniform data structure. That's it. I didn't want any sort of confusion, and so I went with the list because Lisp is actually short for list processor. So just that was pretty important to me as well. And in this implementation, learning is always on, and I know that you have the opportunity to turn it off, but I just didn't get time to sort of think about that yet. But we'll implement that hopefully pretty soon. And many of you guys probably know this guy, Zims, and one of the things he says is talk is cheap, show me the code. So I don't normally like to show code, especially in a presentation, but I think it's just going through a couple of, just the main function, a couple of, let's see if I can get this working. A couple of the things, and show you kind of what I mean by sort of kind of clarity and a really nice mapping from natural language to programming language. So this is essentially, the idea is given your main computing function for how we do temporal memory, it should be the exact same, given the same input, you should get the exact same output as the way it's written in Python. So one of the main differences I talked about is sort of no classes at all. So the way we kind of get rid of this idea of not needing classes is essentially at each moment in time feeding in all the neurons and their associated segments. And so this is obviously very long and very tedious, but you kind of know at any point in time, where your data is and sort of what the state of your temporal network is. So that's sort of one of the major differences. The other one is just kind of the use of the way functions are defined locally here. So just kind of, you can compute your current active neurons they're used to compute the active segments and so forth. You can kind of nicely see how this stuff just moves from start to finish when you get through that. And just the last thing I wanted to touch out without going into a lot more detail is pretty much how you learn in this system. So basically, instead of, we basically only have these 3 learning update functions. And the idea is that you just essentially, as you recur, here's kind of the natural recursion. So we compute, so basically recursion is, just for anyone who's not familiar with it, is once you define a function, you call that same function within the function. So what we're doing is we're essentially not worried about the state of the program at all. And the only thing that we actually output is what goes up into the CLA classifier, so the active neurons. And the rest of the outputs kind of stay within the recursive system. And only, we only need them in order to actually, and as the data sort of flows from your sequences. So yeah, so this is how we kind of continue the process. And I think that's all I got. I don't know what to get into. And so that's it. Is it running? It is not running yet. But I know that it will run. I mean, I've tested all the functions. I just haven't gotten to testing this one big one.
You can't expect them to do HTM and Racket in a hackathon.
No, I didn't know. I just was on the edge of my seat.
But it should run. I'm pretty confident it will.
All right. Thank you.